In this video, I'd like to talk to you about exponential decay in a tabular form, what we call a numeric form. Let's look at a specific example here. We'll do y equals 100 1/2 raised to the x. So in this case, we can tell it's decay because our b value is less than 1, and we can tell our initial value is 100. Let's go ahead and make a quick table of values and take a look at what we got going on here. Plug in 0, 1, 2, 3, 4. All right, so if I plug in a 0, half to the 0 power is 0, times 100 is 100. Plug in a 1, half to the first power is a half, times 100 is 50. Plug in a 2, half to the second power is a quarter times 100 is 25. Plug in a 3, a half raised to the third power is 1/8. 1/8 times 100 is 12.5. And lastly, we plug in we plug in a 4, and a half to the fourth power is a 16th, and a 16th times 100 is 6.25. So now we take a look at the table. The table, what we're looking for all exponential decays are over here, a common first difference, and we can see that each time we go up 1. But in this column, we're not looking for a common first difference. You can see we don't have one. Down 50, down 25, down 12.5, down 6.25. That's not common. We're not looking for a common second difference. That's quadratic. We're looking for what's called a common ratio to find this multiplier, this b value. So the way you can find this is take 50 and divide it by 100. Take 25 and divide it by 50. Take 12.5 and divide it by the previous number, 25. Take 6.25 and divide it by the previous number, 12.5. If I simplify each of these, I get 0.5 or 1/2. This is our common ratio, or our multiplier, and that is the key characteristic in an exponential decay model.